So what happens when the auxiliary equation has complex roots? So if the auxiliary equation that we saw in the previous video has a pair of complex roots, r1 comma 2 equals alpha plus or minus I beta, then the corresponding solutions are given by y1 of x equals e to the power alpha x cosine beta x, and y2 of x equals e to the power alpha x sine beta x. And part of the general solution is then given by y of x equals c1 e to the power alpha x cosine beta x plus c2 e to the power alpha x sine beta x. Notice that I have put a plus dot 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 here because our auxiliary equation has a degree that's higher, or that could be higher than 2. So there could be more roots to that auxiliary equation, leading to other parts of the general solution. So let's apply that to the following example. We want to find the general solution to the homogeneous differential equation y triple prime plus y double prime plus 3y prime minus 5y equals 0. So if we look at the auxiliary equation, that is given by r cubed plus r squared plus 3r minus 5 equals 0. Now notice there's a constant term here, so there's no easy way to factor this by just factoring out an r. So what we have to do there is we have to plug in a couple of values like r equals plus or minus 1, r equals plus or minus 2. And you can verify for yourself that r equals 1 is a solution. So we can then apply long division and this is something that you would have to verify yourself, but you can apply long division and we can factor out r minus 1, and then the rest of our auxiliary equation becomes r squared plus 2r plus 5, and then that equals 0. Now for this part, we have to set that equal to 0. So let me actually write that out. So 0 product rule tells us r minus 1 equals 0. And then the second part, we need to solve r squared plus 2r plus 5 equals 0. And we then get r equals 1 here, which we already found before. And then this quadratic equation we can solve by using the quadratic formula, or we can use completion of the square. So let me do that one time so that you can see that as well. So if we're completing the square here, we're taking a look at the term in front of r, and we take half of that. So you take half of the plus 2, and then you square that. So we have r plus 1 squared. Now, we're introducing, when you FOIL this out, you introduce a plus 1 that's not there in the original one. So we take half of that, put that inside the square, and then we subtract 1 squared from that, and then we add 5 to that. And then we bring the constant to the other side, so we have r plus 1 squared equals negative 4. And then to solve for r plus 1, we're going to take the square root on both sides, and we get r plus 1 equals plus or minus the square root of negative 4. So when we have a negative number, that turns into the imaginary number. So we have r plus 1 equals plus or minus I times the square root of 4, which then simplifies to 2, plus or minus 2i. I'm going to bring the plus 1 to the other side, and I get r equals negative 1 plus or minus 2i. Now, again, you do not have to solve it this way. I would verify that you can solve it with the quadratic formula as well. So now we have our three roots, right? We have our r equals 1, and then the two complex roots here. And what does our solution look like? So for our solution, we have to take a look at that r equals negative 1 plus or minus 2i. And then what we see there is that alpha equals negative 1, and beta is plus or minus 2, but we just always pick the positive value, so we have beta equals 2. And then our general solution will be y of x equals c1 e to the power 1x, that comes from here, and then plus c2 e to the power alpha x, with alpha being negative 1. So that's c2 e to the power negative x, and then cosine of 2x, and then plus c3 e to the power negative x. That's the alpha there, and then sine of 2x. And that is the general equation to this differential equation. Now, something important to note here is that when you look at the number of coefficients here, that is equal to the order of the differential equation, or the degree of our auxiliary equation. So note the number of coefficients needed is equal to the order of the differential equation. So when you see a differential equation that's order 3, to double check that you have all the parts of the general solution, one thing that you can check is to make sure that you've used 3 coefficients. So now, finally in this video, let's take a look at what happens when we have repeated roots. If the auxiliary equation has a real root r of multiplicity m, then the corresponding solutions are given by y1 of x equals e to the power rx, y2 equals x times e to the power rx, y3 equals x squared e to the power rx up to ym of x equals x to the power m minus 1 e to the power rx. And then part of the general solution is given by y of x equals c1 e to the power rx plus c2 x e to the power rx plus c3 x squared times e to the power rx plus dot 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 plus cm x to the power m minus 1 e to the power rx. Now, if the auxiliary equation has a complex root, r equals alpha plus or minus I beta of multiplicity m, then the corresponding solutions are given by, and these come in pairs, e to the power alpha x cosine beta x, x e to the power alpha x cosine beta x squared e to the power alpha x cosine beta x, all the way up to x to the power m minus 1 e to the power alpha x cosine beta x. And we also have all the solutions with sine beta x, namely e to the power alpha x sine beta x, x e to the power alpha x sine beta x squared e to the power alpha x sine beta x, all the way up to x to the power m minus 1 e to the power alpha x sine beta x. So to take a look at this, we have the basic solution when we have that real root r, and then that basic solution gets repeated. And all that changes there is that we have powers of x in front of that basic solution. And that works the same way when we have a complex root. So our basic two solutions when we have a complex root alpha plus or minus beta I, the two basic solutions are e to the power alpha x and then cosine beta x or sine beta x. And you see that is repeated over and over until we've reached the multiplicity of the root. And here as well, all the e to the power alpha x sine beta x. And then the powers of x in front of that basic solution take care of repeated roots. And we'll do some examples in the next video.